Okay, with that, let's try a complete question, a full question. That means from the information given, you are supposed to draw out the pH diagram, and from the pH diagram, you are going to calculate all the useful information, such as your COP and things like that. So let's look at this example 1.2.6. So again, you are given 5 information, okay? 6 information. You are given the 2 pressure, okay, condensing and evaporating pressure. So you are able to draw the top line and the bottom line, okay? And you are given the degree of superheat, compressor discharge temperature, and degree of subcool. So it's a bit different from the previous example, okay, because you are not given T1, T2, T3 straight away. Instead, you are only given T2. Okay, this one is your T2, compressor discharge temperature. Degree of superheat and degree of subcool is not your T1 and T3, but you can use these 2 information to get your T1 and T3. So again, you may want to pause the video and try out this question yourself first. So if not, I will continue with this example. So let's draw the 2 lines, okay? Refer to slide 50, okay? I'm going to draw the 2 pressure lines, okay? Because you need that in order to proceed forward. So first, you know that the evaporating pressure is 0.5 MPa or 500 kilopascal. It is actually this line over here. Okay, so this is your PE equal to 0.5 MPa. Next, you have your condensing pressure, which is 1.5. So 1.5. Okay, this is your PC, 1.5 MPa. Okay, now, how are we going to get the other 3 points? Remember, once you get 1, 2, and 3, you are able to complete the pH diagram. Okay, but right now, we can only maybe get point 2. So, remember, degree of superheat is actually related to the T1. Okay, they are related. So, what you need to know is this temperature over here, which is your TE, your evaporating temperature. You have to add another 10 degrees Celsius because they tell you that degree of superheat is 10 degrees Celsius. So this temperature over here, you add another 10 degrees Celsius, that is your point 1. Okay. In other words, if this temperature from what we see here, right, your TE is around 17 degrees Celsius. Correct? Okay, between 0 and 20 is quite near to 20, so it's around 17 degrees Celsius. So what we can assume that your T1 will be 27 degrees Celsius because you have a degree of superheat of 10 degrees Celsius. If not, if you refer back to the previous so-called formula that I shown just now, degree of superheat is actually equal to T1 minus TE. So degree of superheat is 10, T1 is what we want to find, TE is 17. So from here, you can also find that T1 is equal to 27 degrees Celsius. So with this info, your point 1 should be somewhere between these 2 points, somewhere in the middle. Okay, so this is your point 1. Point 2, no problem. Point 2, you can straight away use the 70 degrees Celsius that is already given over here. So this point is 60, this point is 80. So 70 will be somewhere in the middle. Okay, so this, you can label it, okay, put a cross, label it point 2. So we are going to do the last point, point 3, where you need to use the same idea as how you find point 1. So degree of subcool is 10 degrees Celsius. It means from this point, you need to drop another 10 degrees Celsius to get your third point. So the first question is, what is the temperature at this point? Okay, so that is actually your TC, condensing temperature. Your condensing temperature from here, you can see that it's around 55 degrees Celsius. Okay, because it's between 40 and 60, it's somewhere in the 1/4 away from 60. So it's around 55 degrees Celsius. So if you drop another 10 degrees Celsius, it will be at 45. If not, you can again use the formula. Okay, degree of subcool is equal to Tc minus T3. Okay, so 10 degrees Celsius is equal to 55 minus T3. So from here, if you calculate, T3 is actually equal to 45 degrees Celsius. So with this information, 45 degrees Celsius, it will be somewhere at the 1/4 away from your 40 degrees Celsius line. It will be somewhere here. So that is your point 3. So with these 3 points plotted, you can complete your pH diagram. Okay, so you just need to do the final step, that is to join all these up together. And of course your point 4 is always vertically downwards. Okay, that's your point 4. Then you may want to bold the line that is between 4 and 1 and 2 and 3. Okay, so that will be your completed pH diagram. Okay, that is your first part. Okay, so once you have this, let's do the calculation. Okay, let's do the calculation. So the first thing they want you to find, right, is the COP. Okay, the COP. So you may want to write down what is the enthalpy value for this for the original cycle. Okay, the enthalpy value for the original cycle. So H1, if you refer over here, you draw a line downwards. Okay, somewhere over here, maybe it's around 260 or 265. Okay, H2 is before 300, maybe it's around 290. Okay, so this one is your H1, this one is your H2. H3 is equal to H4, which is over here, around 110. Okay, so you can write down your enthalpy value 265, okay, 295, and 110. So with these 3 values, you can actually start to do the calculation, calculate the COP. Okay, so remember, if you want to calculate COP, what do you need? You will need the, to calculate COP, you will need the Q evap. Okay, you will need Q evap as well as power input. Okay, these are the 2 values you need to find COP. But in order to find work done by the power input, you need to know the work done by compressor. Okay, so you need to know work done by compressor divided by the compressor efficiency. So go ahead and find what is your Q evap and your W comp first. Okay, so Q evap is equal to m dot H1 minus H4. Okay, the mass flow rate is given in the question, okay, which is 0.5 kilogram per second. H1 minus H4. So H1 just now from the pH diagram, okay, we find that it's 265. H4 is 110. So just sub in all this value, 265 minus 110, and calculate. Then similarly, do the same for work done by compressor, where you will take H2 minus H1. Okay, and you will get another answer. So with this answer, sub into this COP formula, you will get the initial COP. So first, if you sub in this, you will get 77.5 kilowatts. That means it's able to provide 77.5 kilowatts of cooling, but it requires 15 kilowatts of work done. Okay, then you will need to find the COP, which is 77.5 divided by 15, but you have to divide by the compressor efficiency, which is 80%. that is given in the question as well. Okay, so that's how I get a 0.8. So if you calculate this thing out, you will get a COP of 4.13. Okay, so that's the calculation. Okay, why is there after? Okay, why is there after at the second part of the question? Because the question actually asks, okay, if you refer back to this slide 50, the question actually asks, what happens when the degree of subcool is increased to 20? That means, right, the degree of subcool instead of 10 degrees Celsius, now it becomes 20 degrees Celsius. Okay, so what is the effect? What is the effect of that? You may want to refer back to this pH diagram. Okay, so if degree of subcool is changed, which point will be affected? Okay, you may want to ask yourself, which of the points will be affected? Is it 0.1, 0.2, 0.3, or 0.4? Okay, so degree of subcool is actually at this part over here, the left-hand side. Okay, so the points that will be affected will be 0.3 and 0.4. Your whole vertical line over here, okay, your line over here will be shifted to the right. Okay, you'll be shifted right-hand side. Okay, because now, right, instead of stopping at 45 degrees Celsius, where will it stop? Okay, it will drop another 10 more degrees Celsius, and it will now drop at 35 degrees Celsius. Okay, because once your degree of subcool over here is changed to 20, your T3 become 35. Okay, your T3 become 35 degrees Celsius once this become 20. So if T3 become 35, where is that point? Okay, it will be somewhere over here. This is 35 degrees Celsius, so similarly you can draw another, you don't have to draw the whole thing, okay? You can just show like that, show it this way. So this line actually shifted to the left. So which value will be affected? The value that will be affected will be H3 and H4. Instead of 110, now what is the enthalpy value? It is below 100 now. So this will be your new pH diagram. You can use 3' and 4', okay, to represent the new values. So the new H3 and H4 become 95. Okay, instead of 110, now it becomes 95. What will it affect? Okay, first it will affect the cooling capacity. Why? Because your H4 is affected. Okay, now your H4 is changed to a smaller value. Okay, instead of 110, it now becomes 95. Okay, so definitely this value over here will change. How about the work done by compressor? Is there any effect? No. Okay, because this formula is H2 minus H1. What actually is being affected is your H3 and H4. So it's actually not affected by this formula. So if you are going to calculate out, only the cooling capacity will change. Compressor work remains unchanged. But your COP, finally your COP will be affected because your Q evap has changed. So from 4.13, it actually increased to 4.53. So what does that tell you? Okay, what is the conclusion? The conclusion is actually your COP has improved, okay, when you increase your degree of subcool. So does that mean that we should try to increase the degree of subcool as much as possible? Of course, that's the most ideal case, but there is also some consequences. Because if you need to have a bigger degree of subcool, you want this temperature to be very low, okay, you will need to do a lot of work at the condenser side. You will have to have a giant fan, you have to upgrade your condensing unit to make sure that it is able to reject a lot of heat at the condenser side, such that it will drop its temperature until this point. Okay, so that's a full question, a complete question together with a pH diagram. Okay, so now let's try one more question, a continuation question from this, the last example, which is example 1.2.7. Okay, 1.2.7. So in example 1.2.6, okay, due to the lowering of your indoor room set point temperature, now, okay, everything remains the same except this. Okay, your evaporating pressure reduced. So instead of 500 kilopascal, okay, now it drops to 400 kilopascal. Okay, it drops to 0.4 MPa, so it's 400 kilopascal. So let me use a new piece of paper. By now, hopefully you are quite familiar in drawing this pH diagram. So I will strongly encourage you to pause the video and draw this out yourself first, okay, before comparing the answer. Okay, that's the best way to check whether you understand what is going on so far. Okay, so you have tried. So let me quickly draw out this pH diagram. So again, draw the evaporating pressure line, okay, which is over here. So PE is equal to 0.4 MPa. And for your condensing pressure, 1.5 MPa, you will be somewhere here again. So a quick one. Okay, so your PC is equal to 1.5 MPa. So using the same idea, okay, of course now your T1 will change already. Okay, it's no more it's not at 27 degrees Celsius anymore. Okay, so now you will need to know what is the temperature over here. So the temperature over here, right, is around maybe 10 degrees Celsius or around 9 or 10 degrees Celsius. So you add another 10 degrees Celsius, it will be very near to 20. Okay, so that will be your first point. Okay, because our degree of superheat is 10 degrees Celsius, so this gap is 10 degrees Celsius. This point is again at 70, no change. Okay, so that's your point 2, point 1, point 2, and point 3. Okay, point 3 will be at 45. Okay, so this is your point 3. So just quickly connect the lines. So once you're very familiar with the methods, right, okay, you can actually draw out the pH diagram very fast. Okay, it's very, very easy. So now this is your completed diagram. So instead of looking like this, okay, which is quite flat, okay, now it becomes this, which is a bit fatter, okay. The gap is wider between the evaporating line and condensing line, okay. And what is the effect of that? Which point actually is being affected? If you notice, okay, the only enthalpy value that's affected is only 0.1. Okay, only H1 is being affected. You will notice that H2, H3, H4, there's no difference, okay, with the change in evaporating pressure. Okay, only H1 is affected. Initially it's at 265. Over here, it actually moved inwards by a little bit. Okay, it's a little bit closer to the line compared to the previous chart. Okay, so this one is around 260. Okay, 260 instead of 265. But there's a very huge effect. Okay, we will see. So please complete the diagram on slide 54. Okay, the one in bold is the original pH diagram, which is having 500 kPa. So the dotted one is 400 kPa, that means shifted downwards. Okay, the whole line shifted downwards. So what is the effect? So before, okay, the initial condition, everything is the same, you get a COP of 4.13. After, okay, the only value that is being affected, remember, is your H1. Okay, instead of 265, now it become 260. Okay, so what is the implication? So remember your Q evap formula is equal to m dot H1 minus H4. Okay, so if H1 is affected, that means this value will change. So it will affect your Q evap. So similarly, work done by compressor is equal to H2 minus H1. So again, H1 is being affected, so it will affect your WCOM as well. So it will affect your numerator, it will affect your denominator, because COP is equal to Q evap over work done by compressor divided by efficiency. So it will affect both values compared to just now where it only affect the Q evap value. So again, just fill in all the numbers that you have. Okay, just sub in all the numbers. So you will sub in 260 now instead of 265 into the Q evap. You will get a cooling capacity of 75. So you notice your cooling capacity reduces. Okay, instead of 77.5, it drops to 75. And for your compressor work, okay, instead of 15, okay, now you require 17.5. Okay, you require more work done. So what is the conclusion? Okay, your COP will be heavily affected. Okay, because you provide less cooling, you need more work to be done. That's why it's not as efficient anymore. Okay, it becomes 3.43 instead of 4.13. So the conclusion is this evaporating pressure, okay, this evaporating pressure shouldn't be decreased. Okay, if you go and decrease this evaporating pressure, the COP will suffer. Okay, the efficiency of your cycle will suffer. So that is to tell you that try not to reduce the evaporating pressure as much as possible. So that is to say, when your room, okay, when you're trying to set a set point at 24 degrees Celsius, that is very ideal. But if you go and change the set point to 23, 22, or even 21 degrees Celsius, it will affect this line. Okay, when it affects this line, it will cause your efficiency to deteriorate, okay, and you will consume more energy. Okay, so you should never set a temperature that is too low for your room set point. Okay, that's the conclusion.